Hello and welcome to this Keep Talking and Nobody Explodes tutorial for Johnson Solids. This tutorial will aim to make this module more viable as basically a diffuser solo, as opposed to a module where you go back and forth with the experts talking about the shapes on a net and which shapes are connected to which other shapes. So there are some terms here that it may be useful to define. I will be using just the shapes that I have on the module to define them, because these are best explained by just looking at the shapes themselves. For the first part of the tutorial, we're going to be looking at J1 through J48, which is just the first 48 solids in the manual. So that'll be all of this first column and these two shapes here, which is pyramids, Cupolae, and Rotundae. So, first we're going to find some. First of all, we're going to define pyramids, Cupolae, and Rotundae. So first of all, we're going to define pyramid. I'll go and find a pyramid. Here we have a pyramid. It's quite hard to see because of the way it's angled, but this here is a pentagonal pyramid. This is a polygon surrounded by triangles that converge to a single point. So we've got a polygon here, a pentagon, and it is surrounded, although it's hard to see, on all sides by triangles, and they all converge to a single point, namely this point here. So we would say that, and this is using a pentagon as its main polygon, it's surrounded by triangles converged to a single point, so this would just be a pentagonal pyramid. Insert a pentagonal pyramid, and we get that is 2. We can get rid of that. Next we will look at this shape here. This will introduce 2 new concepts. So this will introduce the cupola. So here we see a cupola has a polygon surrounded by alternating squares and triangles. Looking at it from this angle, we see a real square. It's surrounded by alternating squares and triangles. There's square, triangle, square, triangle, square, triangle, square, triangle. This point here about the diagonal cupola, we will come back to that later. First of all, but for now, we have this cupola here. So we know that cupola is going to be in the name. On the other side of the solid, we have another cupola. Again, it is hard to see because of rotation, but this is another square cupola attached to this on the other side. So we've got 2 instances of a cupola. So we have a bicupola. It is square, as I said, because the main polygon. So this this polygon here is a square. And if we search this up for our square bicupolas, we have 2 options. We have either an ortho bicupola or a gyro bicupola. So to figure out which one of these it is, we'll go to the definition of gyro and ortho. Gyro is when it has one half gyrated or twisted, indicated by the main polygon, or when it doesn't have that. What it means by having one half twisted, indicated by the main polygon, is whether the the 2 main polygons for each cupola line up. So if we were to connect this square to the opposite square, whether all of their edges would sort of line up. So if you could sort of cut a cuboid through the middle of this, and if it lines up with both of these faces, with that face and the other square face, which you can just about see here. So we want to figure out whether it is gyro or ortho. With Cupolae, it will be ortho if if in the cupola sort of pattern, the squares and triangles, if a square lines up with another square on the other side. Because if this square connects with a square on the other side, then that square will then line up with the square on the main polygon of the square here, which would mean that this edge would line up with the edge of the other square, which means the 2 squares would line up, which would mean they're ortho. In this case, we have this square adjacent to this triangle, which would mean that the two halves are gyrated. You can also sort of see that. You see this edge here, we follow this edge down to here. This is parallel to this edge. We look around, and we get to a triangle which points to a corner of the other square. As you can see just about here. Oh, that's hard to angle. This triangle points to the corner of the bottom square, which means that the two squares are not lined up, so one half is gyrated. So we have here a square, gyro, bicupola. By way of the solid names, as it says here, are ordered by appearance in this list. So you find all the things that apply here, and you go down and name it. This is a square, gyro, bicupola. Anything that has a hyphen after it will be added as a prefix, so gyro, bicupola will be all one word. So we have a square, gyro, bicupola, which is 29. You can hide that. Next, I will go on to this one here. This is another bicupola. It is somewhat hard to see, but we have a triangular cupola here. That's a triangle surrounded by a ring of squares and triangles. On the other side, we have another one, although it's hard to see. You can just about see it there. And you see these two halves are now joined by a ring of triangles. If we go up to here, and we get rid of these, we see that having a ring of alternating triangles separating two halves, the two halves being a triangular cupola and another triangular cupola. So we have a gyro elongated triangular bicupola of some sort, because we have two cupolas with triangles as their main polygons, and they are connected by a ring of alternating triangles. In this case, because this is gyro elongated, this means it is automatically, we have one half automatically rotated relative to the other one, because you see here we've got this edge lining up here. This does not line up with any other edge on the other side, because this is a triangle here. So we've just got a gyro elongated triangular bicupola. Gyro elongated triangular bicupola, which is 44. Now here we have again a cupola. However, it is not a bicupola. It only has one half to it. So first of all, we're going to figure out what we have here. So this is a square as its main polygon. This is a cupola. And we have a ring of alternating triangles separating two halves. Where it talks about separating two halves, one of these halves can be just an empty side. So here we just have an octagon there. So this is separating two halves, being a square cupola and an empty face. So this is in fact gyro elongated, even though it's not immediately obvious that it's gyro elongated because it's not between two halves, but it is between two halves because one half can just be empty. And then we're done with that because we don't have to consider gyro and ortho, because this is only when we have two cupulae or rotundae opposite of each other. So we just have here a gyro elongated square cupola, which is 23. Then we will move on to this here. This will introduce rotundae. So, first of all, we will look from this angle. This is a pentagonal rotunda. Let's see the definition of a rotunda. A rotunda is a polygon surrounded by triangles and pentagons. So we've got here our polygon, our pentagon, and it's surrounded by triangles and pentagons. We can see here we've got triangles and a pentagon, two triangles, pentagon, and this continues around this pentagon, this main pentagon here. We also happen to have two of them, so this is another pentagonal rotunda, because we've got pentagon, two triangles, etc. So we have a bicupola, birotunda, sorry. We also see that these two halves are connected by a ring of squares. This is the definition of elongated. It has a ring of squares separating two halves. This is elongated. And so if we look for our pentagonal birotundas here, we see we've got these two. These are our two elongated pentagonal birotundae. However, you'll see that we have our ortho and gyro prefixes here. So we've got to determine which one of these it is. So we're going to see if one half is twisted from the other. So we're going to see if we can follow an edge from this main polygon here and get to an edge on the other side. So we can do it by going, look at this edge. That would be parallel to this edge here, which is parallel to this edge, which is parallel to this edge, which is now an edge on the opposite main polygon. So that means that these two halves line up, which means they are ortho. So we have an elongated pentagonal ortho birotunda. We go down to here, we see that elongated pentagonal ortho birotunda is 42. Then we can look at this, we can go back to this cupola, we can go back to Cupolae. So here we have a pentagonal cupola, because this is the pentagon surrounded by an alternating ring of squares and triangles. So pentagonal bicupola, and it's a bicupola because we have a cupola on the other side as well. The two halves are connected by a ring of alternating triangles, so it's gyro elongated. And because it's gyro elongated, we can't call it gyro ortho because it is automatically gyro. So we have a gyro elongated pentagonal bicupola. Which is 46. Then we can move on to this. This is another birotunda. This is in fact the same shapes we had before. This is pentagonal, rotunda. We have two of them. They are connected by a ring of squares, so it's elongated. And the two main polygons line up because, as you can see here, we have a pentagon attached to the middle ring attached to another pentagon. So this here would be a elongated pentagonal ortho birotunda. So an elongated pentagonal ortho birotunda, again, which is 42. We can hide that. Now we can go on to this one. This one's a little bit more complicated, but it's still very much the same. It's very much the same thing as the others. We can just look at the different parts of it and figure out a name from that. So first of all, we see we've got a pentagonal cupola. On the other side, we've got a pentagonal rotunda. They are not joined by a ring of squares or triangles, so it's not elongated or gyro elongated. We do not use the term bi here, because we would use this if we had, for example, two cupulae or two rotundae, with one opposite the other. And we can now look at the main polygon. So if we follow this edge here of the pentagon, so we can see, if I find an angle, if we follow this edge here, parallel to this edge, which is parallel to this edge on the other pentagon. So this means the two halves are not gyrated, they are ortho. So we have our name, which is pentagonal ortho cupola rotunda. As you can see here, If both appear in the solid, both names are used. So we call this a pentagonal ortho-cupola rotunda, or cupola rotunda. Which we see here is 32. And finally, we have this, which is something of a special, this is quite a special case, and this can be somewhat hard to figure out if you've not seen this before. So we can't really apply the same things as we did before. We have two halves of something here. They don't seem to have a ring of squares separating them. They don't seem to have a ring of alternating triangles. We don't really see a triangle as a main polygon. We would see that here. We only see a line. It's not square, it's not pentagonal. We can't really say anything about gyro and ortho because we don't know what we're really dealing with yet. It looks like we could have two of something, because it looks like we have this and then a rotated version of this on the other side. These aren't pyramids, since they're not converging to a single point, they're converging to a line. We see here the diagonal cupola, known as the triangular prism, and these do seem to be triangular prisms, is referred to as a fastigium. So what we have here is a bifastigium, and this line here seems to not line up with this line here. They seem to be orthogonal to each other. So that would be a gyro bifastigium, which is 26. And that concludes and that is enough information to be able to do basically any of the pyramids, cupolae, and rotundae. There's not really too much, there aren't too many weird edge cases with these, since they are just made up of either triangular, square, or pentagonal rotundae or cupolae, and they are sometimes two halves joined by a ring of squares or triangles, or they have a bifastigium, which is, as I said, something of an edge case, but as long as you've seen this, it makes sense. Hello and welcome to part 2 of the Johnson Solids tutorial. In this tutorial I'll be covering the modified uniform solids section of the manual. I'll be splitting this into a few parts, namely these 4 parts, which will be prisms, dodecahedra and icosahedra, truncated shapes, and then the rhombicosidodecahedra. These all present somewhat separate challenges when it comes to identifying them. In particular, the rhombicosidodecahedron has a unique challenge to it. So we'll start by looking at this section of the manual. This has noticeably less tags than the pyramids, cupolae, and rotundae section, as there are less, or rather there are fewer things that you can do to these shapes without making them no longer qualify as Johnson solids. So we will start with the prisms. So I've got a reference here for which ones are prisms, so I'll reveal those. I've got some of these hidden because they can get quite large, as you can see with this one here. They can make seeing things from different angles quite difficult. So we can just first of all start with this. So clearly we have a pentagonal prism here. Our main shape is a pentagonal prism. We can see a pentagon here, with a line of squares connecting them, as you see here. Like, this is simply what the net looks like, and the concept of a prism is likely quite well known for you anyway. And we see that we have one augment, which is a pyramid on one of the square sides. So we have a augmented pentagonal prism. We do not need to use parameter because we only have one thing happening. And it's important to note that a pyramid attached to the pentagonal face would not make this an augmented pentagonal prism. It would make this an elongated pentagonal pyramid. when we have our augments, these are never applied to the main polygon, i.e. the face that the shape is named after. So we do not apply an augment to the pentagonal face here, because that's what gives the pentagonal prism the name pentagonal prism. It's this pentagon here. Anyway, so we have an augmented pentagonal prism, which is 52. That's that. We can look at this. We have a hexagonal prism this time. We can have a look at this. So we have a hexagonal prism. We have two augments, so it's bi-augmented. And because we have two augments, we have to decide whether they're para or meta. They are para if they're happening on opposite sides, meta if they're not. As you can see here, they're happening on opposite sides of the solid. So this is a para bi-augmented hexagonal prism. Which is 55. And then we get to this one. This one's quite an important one to have seen before, because upon first glance, this can sort of remind you of one of the shapes in the elementary solid section, which we covered in the next part of the tutorial. Because of how complicated this looks from certain angles, it can be quite difficult to figure out what it is, but this is just a prism. And this is probably the hardest prism to identify. This is a triangular prism. The triangular face, the main triangular face, is this triangular face here. If you look from this angle, you can just about see the triangle and three pyramids attached to the square faces of the triangular prism. That's it. So if we look from this angle, we can see a pyramid. From this angle, we see another pyramid. And if we were able to look from this angle properly, you can see another pyramid. And they're all on this triangular prism in the middle. Because of the size of this shape, it can be quite hard to identify it, and you have to look from a fairly specific angle to see it. But this is a tri-augmented triangular prism, which we have here, 51. The other triangular prisms are somewhat easier to notice because you've got more of the triangular prism shape to it. So that's the prisms covered. Next we have dodecahedra and icosahedra. I'll go and find those, so those are here. I will cover dodecahedra and icosahedra separately. These are very simple. You can just see a dodecahedron here, only pentagonal faces. And these can have augments. So here we have an augment, and we don't seem to have another one. Yep. So this is just an augmented dodecahedron. Since we have one pyramid attached to this dodecahedron. Oh, I might be wrong. No, we do have exactly one pyramid attached to this dodecahedron. So we have an augmented dodecahedron, which is 58. We look at this other one. We look around. We have 1, 2, 3 pyramids attached to it. So this is a tri-augmented, because we have 3 augments, dodecahedron, which is 61. So that's pretty simple. You can see the main shape, the dodecahedron, and then it's quite easy to count the augments. When we go and look at the icosahedron, I've only got one example of this because the icosahedron, the tri-diminished icosahedron, can be somewhat difficult to identify. But yes, here we have a tri-diminished icosahedron. If we imagine each of these pentagonal faces having a pentagonal pyramid attached to them, so the opposite of what diminishing each face does. If we were to augment each of these pentagonal faces with a pentagonal prism, then we would have 5 triangles here, 5 triangles on this other face, and 5 triangles attached here. And then if we count the other triangles, we have 1, 2, 3, 4, 5. So we would have a total of 20 triangles, which would match the number of triangles in the icosahedron. And also we can, if you're able to, you can sort of visualize in your head how this would look. The angles that the triangles are at would continue to look correct. There's also an augmented version of this, where a pyramid will be attached to one of the triangular sides. It's important that it's attached to a triangular side, because if it wasn't, then it would no longer be tridiminished, it would just be bidiminished. So it wouldn't be an augmented tridiminished, it would just be a bidiminished. But because we would place a pyramid on here, it would make it an augmented tridiminished icosahedron. Anyway, so we have here just a standard tridiminished icosahedron, which is 63. Then we move on to the truncated shapes. Let me find those. That's here, here, and here. The truncated tetrahedron, it takes a long time to keep re-rolling these to find this, so I've got an image of it here. This is the regular truncated tetrahedron now, with the hexagonal faces, with one of the hexagonal faces having a triangular cupola attached to it, as opposed to a pyramid on one of the triangular sides. This has a cupola attached to one of the hexagonal sides. This can be fairly, if you're not looking for a truncated tetrahedron, it can be fairly hard to recognize this. But as long as you've seen this, now hopefully this should be more clear. And then we will look at the other ones. So we have a truncated cube. Here we have a truncated cube. This looks like a cube with the corners cut off. As you can see in where is it? This here. So it's octagons with triangles. Truncation is different to things being diminished. Truncation is when you cut corners off. Diminishing is when you remove sections, where a section is something that can be sort of taken off as either a pyramid or a cupola or something similar to this. Anyway, so here we have a truncated cube with 1, 2 augments. So this is a bi-augmented truncated cube. Importantly, we don't say whether it's para or meta, because if it was meta, i.e. if we had an augment here and here, then it would no longer qualify as a Johnson solid. So there's no need to make that disambiguation, so we just call it a bi-augmented truncated cube, which is 67. And then we can move on to truncated dodecahedra. These are the largest shapes on the module. These can get quite big. And these are quite. It's quite easy to tell when you've got one of these, just because of how big it is. But also you can count the number of sides on these polygons here. In this case, we have these decagons and triangles, and then our augments are pentagonal cupolae, where we attached cupolae to each of these decagon faces. And this is another case you can just simply count how many. So we have 1, 2, 3. So we've got a tri-augmented, truncated dodecahedron, which is 71. Very quickly go through this one. We have 1, 2 augments, and they appear... Are they on opposite sides? They do not appear to be on opposite sides, so this would be a meta bi-augmented truncated dodecahedron. And now the last bit is the rhombicose dodecahedron. I've got quite a few of these because there are quite a few variations on this. And a few small naming things that can be quite confusing. So first of all, we'll look at this one. So, actually no, I'll see if I can find a simpler one. I'll use this one here. Actually, that's not simpler, this one. So, in this section of the manual, this is the one where we'll have gyrate sections. We'll have both gyrate and diminish sections on this. So the original shape here consists of pentagons, pentagons which are surrounded by 5 squares with alternating triangles in between them. So if I find a face that's not been gyrated, I'm not able to. If we look at there are no non-gyrated faces. Well, anyway, essentially one of these faces will look very similar, or they will be identical. Oh, here we go, here. So this is this section here, which happens to be coloured in the polygons that are in brighter colour here make up a section which looks very similar to a pentagonal cupola. Essentially, we have a lot of pentagonal cupulae sort of intersecting each other on this shape, and this is what it means when it's referring to a section. A section will be, for example, this cupola here. If you were able to remove this cupola, that would be diminishing because you are removing a section. If you were to twist this, as we can see has been done here, you would, actually no, it's not been done there, has it? Here, on this face, we see that this has been twisted because we have squares lining up on every side of this. Normally, you do not have squares lining up. Normally, you have every square either goes to a triangle or another pentagon. So when you have a line of squares lining up around a section, this means that this section has been gyrated or twisted. And you often have to look around the entire solid trying to count these. It can be fairly hard, but looking at it as sets of squares that are touching in a ring like this can make it easier to find them. So we've got one here, another here, and let's see, do we have another one? Yes, we do. We have one at the back here. It can be sometimes be hard to see. You have to tilt the module in annoying ways. But essentially, we have 3 sections twisted here. So this is a tri-gyrate rhombicosydodecahedron. Which is 75. And if we look at this one here, this will give us examples of things being diminished. So we have a section being diminished, revealing a decagon. So we have a diminished section. We also have a gyrate section, this section here. You can see the ring of squares around it. We'll see if we can find any other gyrated sections. We can. This section here is gyrated. You can see 1, 2, 3 sections or pairs of squares around here. This has been gyrated. So this is a bi-gyrate diminished, because as we can see here, the prefixes bi and tri can appear after augmented or gyrate when directly applied to diminished. So if this was diminished twice and gyrate, we would be able to call it gyrate bi-diminished. In our case, we just have a bi-gyrate diminished. So this particular point here does not apply currently, but we have a bi-gyrate diminished rhombicosydodecahedron. Importantly, we do not need to say whether this is para or meta, because there are in fact 3 things happening. There's 1 section being diminished, and 2 sections being gyrated. So there's no need to add para and meta. So this is just a bi-gyrate diminished rhombicosydodecahedron. Oops, that's meant to be just diminished. Bigyrate diminished when we're close to dodecahedron is 79. Hello and welcome to the third part of the Johnson solids tutorial, which will be covering J84, J92, the elementary solids. These solids, while they have somewhat systematic names, they do, first of all, include some solids that do not fit with the rest at all, and so they have unique names. And by virtue of what it says here, the fact that they cannot be constructed in the way that outlined above, they're sort of, there are fewer general things that you can say about them, and they sort of need to be looked at case by case. And since there's only 9 of them, this tutorial will just cover all 9 of them individually, and showing you the reasoning that you can use to determine which one it is. So, first of all, we will start with the snub disphenoid and the snub square antiprism. These two do not go by any of this naming scheme, they are simply these two shapes here, with the net shown. The snub disphenoid can be found over here. It is exclusively triangles, there are 10 of them, and there's not really any great way to sort of reason for the... I don't know of a good way to reason for the naming. The only thing that I can assume is that sphenoid is some derivative of the word spheno used here, but I don't really know. All I can really say is that from this angle you can see there is some sort of diamond shape with 2 triangles pointing out to the top left and top right, and here the same shape with them pointing out the bottom left and bottom right. And you could also say that if you look at the bottom here, you sort of have these 2 triangles here. If you look opposite that, you have 2 triangles here and here, and then you sort of have a ring of triangles separating those halves, is another way that you can look at it. Or you can look at it from, say, what angle was it? This angle, sort of hard to see because of this being in the way, I'll remove that. From this angle, you sort of see a tall pentagon, I suppose. There's not really any fantastic way to identify this, apart from the fact that it's exclusively triangles, and it's very small. And notably, it's not a tri-augmented triangular prism, which it can be somewhat easy to confuse with a tri-augmented triangular prism, because that shape also only has triangles. But anyway, so this is a snub disphenoid, and that is 84. We can move on to the snub square antiprism, which is over here. So I think this one's a bit easier to identify. You've got a square, and you've got another square on the other side, which is hard to see, but it's right there. You've got, from this angle, you can see a ring of, is that 8? No, that's a ring of 12 triangles. From the other side, you would see the same thing. And I mean, the way that I would normally describe this is the one that sort of looks like a burger, I guess. Like it looks like a lot of triangles in between 2 squares. And there's not really much more to say about this. I don't really know about the reason for this naming. I can see why it's called a square something because of the squares. I don't really know what it means by an antiprism. It's probably something to do with all the triangles that are between the 2 squares. No idea, but this is what the snub square antiprism looks like. Quite notably, it has this square with the 4 triangles pointing away from it, with the 4 pairs of 2 triangles sort of pointing outwards from each other on the corners. So anyway, that is 85 from the snub square antiprism. Then we go on to the coronas. So we will quickly look at some definitions. So in the elementary solids category, we have augmented, which is when a pyramid is attached to a side. Triangular, which is when a solid has a hexagon. This will make more sense later. Bi is when we have two instances of something, as before. I will skip over lunar for now. I'll skip the cingulum. For a corona, we have a crown of 8 triangles. The exact appearance of this can be seen in 86, the sphenocorona, so that's here. Oh no, we can't actually get the correct angle on this one. You able to get the back of angle on this one? No. There's not really a good way to get a good angle on it. However, essentially what it looks like is it is an arrangement of 8 triangles in something of a crown shape. The naming for this, okay, we can just look at the rest of the naming for this, because there are other things that you can do even if you don't know that it's a corona. Like, you're able to count the triangles somewhat. We can sort of tell that there are the shape, yes. You're sort of able to look around and see how many triangles there are. It is quite hard, but you can just about do it. So it has a crown of 8 triangles, and we also have luna. Luna is what's used to mean a square with triangles on opposite sides. So here we have 2 of those, and they're actually neighbouring each other, which has a specific name, which is spheno. So we can see we have that with this square and this triangle and this triangle, and we have another one with this square, this triangle, and this triangle. So we have 2 neighbouring instances of lunae, which is, and we use spheno to refer to that. And then we also have a corona attached to those. The corona is hard to see with this particular shape, but if we look from this angle, we can sort of see those 3 triangles sort of at the bottom left of the shape as we're looking at it from this perspective. And we can sort of see symmetry. There's not really a good way of looking at the corona properly for this shape, but essentially you can see symmetry here down this sort of bottom left to top right diagonal, which sort of tells you something about the shape. There's not really much more to say about it. It's very hard to see it properly. But yes, so we have 2 lunae next to each other, so that's spheno. So we can search up spheno. And we have the option of quite a few things, but this is not augmented because there's no pyramid attached anywhere. It's not a megacorona because the megacorona has 12 triangles and there's simply not enough triangles in the corona here to even think it's 12 triangles. And also, just a note, is that the corona and megacorona do not count triangles that are part of a lunar shape. So these 2 triangles and these 2 triangles are not part of the corona. Actually, there might be a better angle from here. Not really. So this shape is a sphenocorona. We can move on to the augmented sphenocorona. This is showing the shape we just had, but at a different angle, and with this augment here. This is a pyramid attached to a square face. If we look at this from, which angle was it? It's somewhat hard to see because of the augment sort of confusing things, but if if we look at it from this angle, we can sort of see the shape of the corona. If we look at this here, the shape of the corona, it has, that's too wide, it has this diamond here, as well as these shapes on the sides. So this, every single triangle you can see right now is part of the corona, and on the opposite side of the corona we have one square with two neighbouring triangles, being this triangle and this triangle, and another square with two neighbouring triangles, being this triangle and this triangle. However, there's an augment on that square, so we can't actually see the square. But this is an augmented sphenocorona, because we've got spheno, the two neighbouring lunae, and the corona, as we saw from some angle that way, which makes this 87. Remember that. Then we can move on to the spheno-megacorona. So the megacorona, as we saw up here, is a crown of 12 triangles. Which one's the relevant one? Let me have a look. 88, which is over here. So this is it's a lot easier to see the shape of this one, in fact. If we look from this angle, we can see that same diamond shape we saw in the normal corona. We've got this diamond shape, as well as just the rest of what is visible in this diagram currently. We've got this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and yes, so these 10 other triangles. So 1, 2, 3, 4, 5, those triangles on that side, and the 1, 2, 3, 4, 5 triangles on this side, as well as the two triangles here, are what make up this entire megacorona. It's a bit more of an obvious shape because of the size of this and the orientation of it. Then we can see how it's spheno because it has two lunae next to each other. From this angle we can see square, triangle, triangle, and square, triangle, and there is a triangle attached to that on the other side, although it's not very easy to angle it so you can see it. But this here is a spheno-megacorona. Then we can move on to the hebaspheno-megacorona. The term hebaspheno refers to when there are three instances of lunae. So if we look from this angle, we can once again see the megacorona. We've got the two triangles here, then 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. However, if we look around the shape, we see one luna there, being this triangle, this triangle, this square, and this other triangle. Then a second luna, this triangle, this square, and this triangle. Then a third luna over here. Is that what it is? Yeah. Being this square, this triangle, and that triangle to the top left of where my cursor currently is. And because we have three of these, we have a hebaspheno megacorona. So we look down here, that is 89. Noting again, the megacorona is these two triangles, these 5 triangles, and these 5 triangles. None of these triangles are involved in the lunae around the shape, because if they were, they would not be counted as part of a megacorona. Then, moving on to 90, we have the disphenocyngulum, which is over here. We need to define what it means by dispheno and what it means by cyngulum. So, we have dispheno, because of this here. We use di instead of bi to prefix spheno. So if we have two instances of a spheno section, which itself is two neighbouring instances of lunae. So we can see that here we have two neighbouring instances of lunae, being this shape and this shape. And then on the other side we have the same thing, two neighbouring instances. Where's the shape? Over here. That's not a shape. Over here. And we've got another two neighbouring instances with this one and this one. So this is dispheno. And then we look, so this looks like gyro elongation connecting two halves. However, for elementary solids it's called a cyngulum. This is related to gyro elongated, as I said. It has a ring of alternating triangles. As you can see, this is a ring of alternating triangles. You can't really see all around it, but this is a ring of alternating triangles. So we have a disphenocyngulum. Which is 90. Then we move on to bilunar birotunda, which is over here. So, the bilunar comes from this lunar and this lunar. And the birotunda, if we go back up here, the rotunda here means the exact same things it did before. A section of a pentagonal rotunda, a vertex surrounded by two triangles and two pentagons alternating. It is not completely clear to me how the name birotunda comes about here. I can assume that this is considered a rotunda section, and that the copy of this on the other side is also a rotunda section. So, in some way, one second, I'll get rid of these. So we have a bilunar, because there's one lunar, there's another lunar. Birotunda, there's one rotunda section, and there's another rotunda section. So here we have a bilunar birotunda. This is a fairly distinct shape anyway, so for anyone who knows what they're doing, it shouldn't be too hard to identify that. And the final one we have is a triangular hebespheno-rotunda. So first of all, the triangular, it says in the manual, for this exact meaning is unclear. If the solid has a hexagon, which would be referring to this hexagon here. However, I think that the triangle here is likely where it gets its name. So this is triangular. We look for lunae. We have one lunar visible here, another one visible here, and there is a third visible, just about visible here. So this is hebespheno. There's no cyngulum, there's no corona, there's no megacorona. There is a rotunda, which is right here. The way that the triangle, this top triangle, is part of the rotunda is somewhat confusing because no other rotunda looks like this. However, this is in some way a triangular rotunda. So we've got a triangular rotunda here, and this is hebespheno because there are 3 instances of lunae. So we have a triangular hebespheno rotunda, being 92.